Thank you very much, Rock, and thanks for the invitation. It's a privilege to be here today and to talk about a topic that I've spent quite a bit of time over the last years called generalized pairwise comparisons. And as you will see, I will argue that this is a good statistical method for more patient-centric analyses of our data, particularly in clinical trials. So my background is in biostatistics. I have a PhD from the Harvard School of Public Health in biostatistics, and I work for a company called IDDI, International Drug Development Institute in Belgium and the US. And also I have a part-time teaching position at the University of Hasselt in the north of Belgium. So let's go to the talk itself, and let me show you my agenda. So I will actually develop the theory of generalized pairwise comparisons, which, as you will see, is actually very simple, very powerful, but very simple at the same time. I will introduce a new measure of treatment effect that we call the net treatment benefit. And then I will illustrate this theory in 3 different examples. One in which I will show that GPC, generalized pairwise comparisons, allow you to do 2 things at once: increase the statistical power of the tests that you use to analyze data, and also increase the clinical relevance of the analysis. And that's why it's a good method for patient-centric analyses, because you can focus on what is really clinically relevant, as I will show. I will also show that this method can be used for rigorous benefit-risk analyses. And then I will finally give a few words on why this method is preferable in at least some cases, to multiple testing procedures. And then I will conclude. So let me start with the theory. The theory of generalized pairwise comparisons goes back to the well-known Wilcoxon rank sum test. You've all seen this test in your classes on non-parametric inference. And the Wilcoxon test consists of comparing 2 groups. And we will suppose that we are in the context of a randomized clinical trial where one treatment is given to a group of patients, and another treatment, maybe the control, is given to the other group of patients. And we will call X and Y the realization, the variables, that the outcome that we measure in these patients. We call it X in treatment T and Y in control C, but it's in fact the same outcome, obviously, that we measure. It can be anything, as we will see. But let's suppose initially that we have a continuous outcome, which is measured on these patients. And we call the realizations of these variables X1 to Xn for the N observations in the treatment group, and Y1 to Ym, M observations in the control group. Excuse me. So you remember that, or you may not remember, but in fact, the Wilcoxon test consists of ordering all these realizations, all these observations in increasing order, and then we let Ri be the rank order of the ith element of this ordered list. And then when we have tied values, then we assign a rank which is equal to the midpoint of these ranks. To untie the observations, if you like, you give them the mid-rank, and then you calculate the sum of all these ranks over all these observations, and in the treatment group. So you take only the N observations of the treatment group, calculate the sum of the ranks of the observations in the treated arm, and then this sum of ranks is a statistic, which we call U, and it has a known distribution under the null hypothesis. There are tables for these. We used to use tables in the old days. Of course, now everything's computerized, but we also have an asymptotic distribution for the statistic, which is a U statistic, hence the choice of calling it U. Mann and Whitney, 3 years after the Wilcoxon test appeared in the literature, Mann and Whitney showed that, in fact, you can reach the exact same test not by ranking the observations, but by doing pairwise comparisons. So it's the exact same test, but using 2 completely different approaches. One based on the ranks of the observation in the 2 group treatment arms, the other one with doing pairwise comparisons. And it is this particular approach, the Mann-Whitney approach, that we will use throughout this talk. So the Mann-Whitney approach consists of doing all pairwise comparisons with 1 observation from the treatment group and 1 observation from the control group. And then remember we have a continuous outcome, and let's suppose that a larger value of this continuous variable is better. Then if xi is larger than yi, that means the treated patient in this pair does better than the control patient. And in that case, we give score to this pair, and we call this score uij. The score is set to 1 if xi is larger than yj. The score is set to 0 in the opposite situation, then that when the control patient does better than the treated patient, then we give a score of 0 to that pair. And then if we have a tie, we just give a mid-score, which is 1/2. And then again, we calculate the sum of all these scores. And in fact, this sum has a known distribution under H0, and this statistic Q is exactly the same as the Wilcoxon statistic. So we have two different tests. Again, they use two different approaches, but they come to the exact same test statistic U, which has the same distribution. So the idea of this talk is to generalize this concept and to go beyond the Wilcoxon Mann-Whitney test. How can we generalize this? We can generalize in different ways. The first way in which we can generalize is to say, well, if I can compare xi to yj, it doesn't matter what rule I use as long as I can decide if xi is better than yj. So not just larger for a continuous outcome, but just better. And of course, that could apply to any type of variable, as I will show on the next slide. And so as long as we can use these operators better than, worse than, and equal to, or similar to, then I can again calculate the U statistic just as before. And this U statistic, again, has the same distribution, which is a U statistic distribution. So when we look at different types of outcome, we could have an ordered outcome with a larger value preferable. It doesn't have to be continuous, could be categorical. In this case, we can use the Wilcoxon test, but it applies then to a categorical variable. For a binary outcome, I can use this too. If I denote y a success and 0 a failure, obviously y 1 is greater than 0, so I can use the Wilcoxon test on a binary outcome. For a time to event outcome, Ed Guillen, much later, showed that, in fact, you can use the Wilcoxon test, but you've got a problem with censored observations. And so you have to adapt the Wilcoxon test to account for the fact that some observations are censored, and that can be easily done. But for other types of outcomes, we could have outcomes that are completely arbitrary. We can then use an arbitrary definition of what we mean by better than or worse than. We can go beyond that. Suppose that, again, we go back to a continuous outcome, and suppose now that we will claim that there is a difference between the two outcomes of the treated patient and the control patient only if the difference between the two exceeds a certain threshold that I call delta here, which I call a threshold of clinical relevance. Suppose, for example, I look at survival data and I want to compare two patients, but I'm going to call them different survival only if one patient has a longer survival by at least 6 months compared with the other patient, or 12 months, or any type of difference that I'm interested in given the context of this particular experiment. So delta can flexibly be chosen as a threshold of clinical relevance. So that's another generalization of the test. I can even go beyond that and look at multiple outcomes. And this is where the method really becomes of interest, because instead of looking at one outcome at a time, and I can do several Wilcoxon tests on different outcomes, I can actually look at several outcomes in the same test. Suppose I denote by K now, the outcome that I'm interested in. I can do the same scoring for each and every one of the K outcomes that I'm interested in. And so I will end up with capital K scores. And what I will do is to indeed sum the scores across all these K outcomes, the same score as I had before. And that will give me a generalized Wilcoxon test, which then will look at all the outcomes simultaneously. This test was proposed, again, more recently by O'Brien. Not so recently, actually, in 84, 30 years ago, 40 years ago almost. And so this test was not much used, but it's a nice test to combine several variables in the same analysis. The big problem of this is that, of course, if you just do the sum of all these scores. You put all these outcomes on the same level as if they were equally important. And in general, that's not the case. When you have multiple outcomes in an analysis, typically the outcomes are different from each other, and some of them are more important than others. So you could actually handle this through weighting, but weighting is difficult because it's very arbitrary. And there is a more natural way of doing it, which is on the next slide. It's actually ordering the outcomes. So you would have an outcome of first priority, followed by an outcome of second priority, and so on. And the scoring here would be just as before, except you would look at the first outcome first, the outcome of highest priority first. If you could classify a pair as a win or a loss, a win is a pair that favors treatment, a loss is a pair that favors control, or as a tie. If you can classify the pair on the first outcome, you're done. You stop there and you go to the next pair. If you can't classify this pair because the two values are equal or the two patients do equally well on that outcome, then you use the second outcome to untie this pair. And again, if you can untie the pair, then you have a win or a loss. Otherwise, you continue. And you can go through a long list of outcomes if needed, and then have a score that, in fact, looks at the totality of the outcomes, but in prioritized order. And this, I would show an example of this. This can be extremely helpful if a natural order can be determined for the outcomes. Then let me come to measures of treatment effect. A natural thing to do when you have this U statistic is just to look at the number of wins minus the number of losses over the pairs. That is nothing else than the Wilcoxon Mann-Whitney U statistic. And that we call the net treatment benefit. So it's a very natural statistic because it's exactly equal to the Wilcoxon statistic. So that's the net treatment benefit. And I will come to the interpretation of that statistic in a moment. But before I go there, let me mention some other statistics, test statistics that have been proposed. The win ratio is just the number of wins over the number of losses. And that's another measure of the treatment effect. It's a relative measure. This is an absolute measure of treatment effect. This is a relative measure of treatment effect. And in fact, it's a good statistic because it happens to be equal to the inverse of the hazard ratio if you are under proportional hazard. So the win ratio has a simple relationship to the hazard ratio. So it's a familiar statistic, but looking at the time to the highest priority outcome first instead of the time to first event if you have multiple outcomes. So it's a generalization in a sense of the hazard ratio. The win odds has been proposed because, as you see here, we ignore the ties. And this is sometimes a problem. So when ties need to be taken into account, then the win odds is a modification of the win ratio that looks at the ties as well. And so this has a proper interpretation as an odds. Note that the net treatment benefit has a simple relationship with the win odds. But from now on, I will concentrate on the net treatment benefit rather than the other statistics. So let me take a very simple example just to show you that the calculations needed to calculate these treatment effects are very, very simple. Suppose we have 12 observations, 6 in the treatment arm and 6 in the control arm. We look at how many patients do better in the treatment than in the control. These are the green arrows here. And there are 23 such pairs. Then we look at the losses, how many patients do better in the control group than the treatment. Then we have 9 such pairs. And then we look at the ties. There are 4 ties. So we have 36 pairs in total, 6 by 6, multiplied by 6, that's 36. And then 23 wins minus 9 losses, that's equal to 14 divided by 36. That's a net benefit of 0.39. Then you can also calculate the win ratio and the win odds. But let's focus on this 0.39 net treatment benefit. You might ask, what does that mean? What is the meaning of that treatment effect? In fact, the net treatment benefit is simply the probability that X will be greater than Y minus the probability that Y is greater than X, obviously. So it's the net probability of a better outcome in one treatment group than the other. If you like, more specifically, is the probability that a patient taken at random does better in the treatment group does better than a patient taken at random in the control group minus the probability of the opposite situation, that the control patient does better than the treated patient. So it has an interpretation in terms of a net probability of doing better. There is a relationship between the net treatment benefit and another measure of treatment effect called the probabilistic index, which is simply the probability that X is greater than Y. You may have seen this before. And this is something that has been studied in great detail in the statistical literature. It's also called the proportion of similar responses, the concordance index, which is due to Frank Harrell, the probability of overlap, and the area under the ROC curve. So all of these measures of treatment difference are in fact the same thing. It's the probability that X is greater than Y. And we look at a transformation of this 2 times the probabilistic index minus 1. And the advantage of this particular net treatment benefit transformation is that it's equal to -1 if control is systematically better than treatment. It's equal to +1 if treatment is always better than control. And it's equal to 0 if there is no treatment effect, which is quite cool, because then it's kind of intuitively obvious that a treatment effect of 0 means no treatment effect. Treatment effect of 1 means the treatment always does better than the control. I won't go into the details. I mean, I said it's very easy to calculate these test statistics, not so easy to, do inference on them and to calculate confidence limits for the estimated treatment benefit and so on. So, I mean, the technical details are shown on this slide. You can do lots of approaches for inference and estimation. And here are a few that have been proposed over time using either permutation test, bootstrap distributions, or asymptotic distribution of used statistics. So here are the references, and I won't dwell on this because I think it's more important to talk about examples. One other aspect that I will not go into today for lack of time is how you adjust the net treatment benefit for censoring. You may remember from your survival course that the Guillen generalized Wilcoxon test is actually biased in the presence of censoring. And we almost always have censoring when we do survival analysis. That's why there is a whole field of theoretical developments devoted to survival analysis. And it's been shown by Efron initially and then by others that you can remove the bias in the estimated treatment effect by different approaches. There is a naive approach that is very easy to adapt for the Wilcoxon test, which is to look at just the informative pairs. In other words, ignore the ties, and then you get an unbiased estimate of the net treatment benefit or the win ratio. Imputations can be done using the survival distribution, and this is what Efron initially suggested, and then Pito and Pito also used this approach for their log rank test, and then a whole range of tests were proposed based on that concept of using the Kaplan-Meier estimates of the survival function to adjust and remove the bias from the net treatment benefit estimation. And you can also use something that was more recently proposed, the inverse probability of censoring weighting, to account for the censoring. But I wanted to go to the applications and leave enough time for discussion. So let me first show you a really cool application, I think. This is one that we were, an analysis that we were asked to do. And this concerned patients who are treated for a certain form of cancer, of advanced cancer, and they are treated aggressively. And they may experience severe toxicities from that treatment. I don't want to give the details because this is to some extent confidential, but you probably know that in cancer patients, the toxicities are graded on a scale called the WHO scale. Grade 3 is severe toxicity, grade 4 is life-threatening, and grade 5 is lethal toxicity. The patient die of a toxicity. Here, for this particular example, the traditional primary endpoint for comparing a treatment to a control is to look at the incidence of grade 3 or 4. In this case, there were no deaths, but grade 3 to 5, let's say grade 3 or worse toxicity. And just looking at the incidence means you have to do a comparison between two proportions. Proportions of patients who got grade 3 or worse in one group versus the same proportion in the other group. And this, of course, is a feasible analysis, but it's not terribly sensitive because comparing proportions, as we all know, is not a sensitive test. We ignore in that test the severity. Is it grade 3? Is it grade 4? Is it grade 5? That matters. How long did it last? Some toxicities in this example, again, lasted for a few days, but in some patients, it lasted for several weeks, and in some cases, even months. So, I mean, that's quite different. Having that severe toxicity for 2 days isn't the same as having it for 2 weeks. And then finally, the time to onset is always interesting as well, because a toxicity that occurs later is preferable than a toxicity that occurs immediately or very soon after beginning the treatment. So in any case, here is an example that is kind of made up. The numbers are made up, but it's quite close to the actual situation. And we look at prioritized outcomes here. Instead of looking just at the incidence of grade 3, 4, we look first at how many patients had grade 4. And so we do the pairwise comparisons on grade 4 toxicity, yes or no. In that case, we can determine the number of wins and the number of losses. In other words, patients who have a grade 4 in the control arm, but not in the treatment arm, these are the wins. Patients who got a grade 4 in the treatment arm, but not in the control, these are the losses. The difference between these two, 6%, is the net treatment benefit on that outcome. In other words, it's the proportion of patients who did better on treatment and control. It's in fact simply the difference, between the proportions of grade 4 in the treatment arm minus the control. That's 6%. Then we look at grade 3. In other words, patients who had grade 4 now are no longer in the analysis. If you have a pair where two patients had grade 4, that pair is not determined, because they both had grade 4. If you have a pair that none of the patients had grade 4, again, that pair is a tie, you go to grade 3. So the pairs that are not classified here, the ties, will be untied by the grade 3. And here again, we have a number of wins, losses. The difference is the net treatment benefit for that outcome. Duration, for those patients who had, a tie for grade 3 or grade 4, those patients, then we look at the duration. If two patients had grade 4, in which of the patients was the duration longer? Was it the treated patient or the control? And so that gives us a 7% net treatment benefit and time to onset 3%. So the point of this slide is to show that the comparison of the incidence would be just, something like this 6 plus 3%. That's a 9% difference in response rates, in toxicity rates. But if you look at the totality of the evidence, including duration and time to onset, you get to a 19%. The next slide shows this a little more clearly. Here we have the net treatment benefit here and the p-value of the test for that outcome and all previous outcomes. In other words, we test the cumulative net benefits here. And what you can see is that you get a non-significant p-value for grade 4, a non-significant p-value for grade 3 and 4, which is this guy here. And then it's only when you add the duration and the time to onset that you get significant differences between the treatment arms. In other words, we've increased the power of our test because we've included 4 outcomes instead of 1. And we've made it more clinically relevant because we now look at what matters to the patients, not just the fact that they had grade 3 or 4, but how long did it last and when did it occur? So this is a more powerful analysis, but it's also a more relevant analysis in clinical terms. Second example I wanted to discuss briefly, I'm looking at the clock. Okay, I'm doing good. The next example I wanted to discuss is benefit risk analyses. As you know, benefit risk analyses are typically done by looking at the benefits and doing marginal analyses of each of these benefits, and then looking at the harms and looking marginal analyses of the harms, the toxicities, the side effects, and so on. And then the benefit risk is kind of looking at, the benefits and the harms and doing some kind of a combination of these two. Now, mathematically, this doesn't fly because you ignore the correlation between these outcomes. And you can't just look at the marginal analyses of the positives and the marginal analyses of the negatives and then combine these two. They're not just combinable because, again, it depends on the correlation. So I'm going to show this using a very simple example and show why the GPC analysis is better than doing marginal analyses of benefits and risks. So suppose I have two treatment groups, treatment and control, and I'm looking at benefit, and I'm going to take the super simple example of a binary outcome that quantifies benefit, the response rate. So response rate is 0.5 in the treatment arm and 0.2 in the control. So 50% of patients respond in the treatment versus 20% in the control. That's a large treatment benefit. It's 30% better. More patients respond in the treatment arm than the control. And the toxicity, I'm going to assume just for simplicity that 60% of the patients have a toxicity, let's say severe toxicity, for example, in the treatment arm, and no patient has a toxicity in the control. Let's assume. So that's a big difference against the treatment. So if you do this marginal approach, you have a 30% improvement due to the efficacy of the drug, but you get 60% toxicity rate. So overall, it's a minus 30%, if you like, benefit risk, which means what? No one would do this calculation, but that's the only one you can do with marginal results. Now, if you do a GPC analysis of this, you can actually look at the net treatment benefit as a function of the odds ratio. So you look at the cross-classification of efficacy versus toxicity, and sometimes efficacy is fully correlated with toxicities. Sometimes it's the opposite. The toxicity is completely unrelated to the efficacy. And I will come to this in just a moment. But depending on this odds ratio, you see that the net treatment benefit, the black line, can go from negative to positive if you prioritize the response over the toxicity. So suppose I'm first interested in improving response rate, even if it's at the price of toxicity. So first priority outcome is response. Second priority outcome is toxicity. The blue line is the net benefit at a 30% benefit in favor of the treatment. Remember, it was 50% versus 20%. That's a 30% benefit. But then the red line is in fact the second outcome. So it's analyzed conditionally on not having a tie, on having a tie on the first outcome, which is the response. So for patients who are tied on response, then I untie them with the toxicity. And this is the dotted line here that I see. The sum of these is in fact the black line. So the sum of the blue and the dotted red line is the black line. That's the total net treatment benefit. And what I see is that if there is no correlation between the two, if there is, the odds ratio is equal to 1, that means no correlation between the efficacy and the toxicity, the net treatment benefit is equal to 0. Whereas if there is a negative correlation, if you have an odds ratio that becomes smaller and smaller, net benefit is actually negative, but it's positive if you have a positive correlation. Now, what do I mean by these correlations? Now, if the odds ratio is greater than 1, then that means that patients who respond also are likely to have a toxicity, right? So that's a positive correlation between the two outcomes. And there are examples of this in cancer treatment. For example, if you give an inhibitor of the EGFR pathway to patients who have a lung cancer or some other forms of advanced disease, in fact, they get skin rash. They may get skin rash. And the skin rash is a toxicity that's due to the effect of this drug. The toxicity is associated with the efficacy. Patients who have skin rash are very likely to also respond to treatment. So it's a marker of efficacy in a sense. And that, of course, is something that can happen. You can also have a case where there is absolutely no relationship between response and efficacy. Suppose you give anthracyclines to patients with, again, advanced forms of cancer. Anthracyclines are cardiotoxic drugs, but the cardiotoxicity has nothing to do with the anti-tumor effect. So the fact that the drug works is independent of whether the patients will have a cardiac toxicity. It's more the cardiac predispositions, the patients who are frail to begin with, who are more likely to have the toxicity. And finally, there are cases also of a negative correlation. In other words, the patients who benefit from the drug are those who do not have a toxicity. And this is also seen in cancer treatment. For example, in patients are treated with irinotecan. In fact, it's shown that some patients have very severe toxicities from irinotecan, and so such that you have to stop the drug. They just can't tolerate it anymore. And then obviously patients who have the toxicity will have less efficacy because they receive less of that drug. So all of three cases, that I showed on my graph here, the three situations can occur. And so it's important to account for the for this relationship between the two, or the correlation between the two outcomes. Now, of course, if I now said, as a patient, I would prefer not to have a toxicity. I don't care much about response, but I don't want a toxicity. You could do the exact opposite analysis, which is to say, I'm going to prioritize toxicity first. I want to avoid toxicity. And then for patients who have either both toxicity or non-toxicity, then I will untie these ties with the efficacy outcome. And in that case, the net treatment benefit will be very different and will be against giving this treatment, obviously, because it's so toxic. The last example I wanted to discuss briefly is how GPC, generalized pairwise comparisons, can replace, in some cases, multiple testing procedures. So I'm going to use an example that I'm taking from an actual trial. I'm not going to say what trial, but and so I've hidden the treatment names and so on. But this is a real trial that was done by a pharma company. And in this particular case, they had 3 randomized groups, a control group, and then 2 experimental groups. But importantly, experimental 1 was the treatment that for some reason they preferred based on preclinical evidence and so on. Experimental 1 is the one they truly believed in. And then they had experimental 2 as another experimental arm versus the control. So the comparisons of interest here obviously would be A versus C. That's the preferred comparison. Also B versus C. And then the trial wasn't powered to detect the difference between A and B. So A versus B was not powered. In terms of the outcomes of interest, this was in cancer patients. The progression-free survival was by definition the primary outcome. So they pre-specified that PFS, progression-free survival, would be the primary outcome, and OS was a sort of key secondary. So here is the testing procedure that they proposed. PFS would be tested first at the level of 5%. For A versus C. Remember, that was the primary comparison of interest. Is A better than C? If that test succeeded, then they would test the PFS of B versus C at the 4% significance level, and they would test OS of A versus C at the 1% level, right? And if this test succeeded, then they would compare B versus C in terms of OS. Now, note here that the alpha level to use for the OS comparison of the primary comparison of interest, A versus C, is 1% if the PFS fails on the other treatment and 5% otherwise. That is ridiculous. You cannot say that you will test your survival in the preferred comparison at different significance levels just because you have another treatment in the trial. It doesn't make sense. I think it doesn't make sense. Much better would be to use generalized pairwise comparison and say that you're going to look at time to death first, followed by progression. So for 2 patients who have died, you look at their progression time. But for two patients, one of whom has died and not the other, then you take the time to death for this. So this is the time to worst outcome rather than the time to first outcome, which is done in PFS. So I think one has to think in terms of more what's relevant for the patient. And what's relevant for the patient is first to avoid dying or to delay dying. And then secondly, to delay time to progression, not the other way around. And so the GPC approach would eliminate the need for this ridiculous testing procedure and would actually make it much easier to then test each of the 2 groups using a multiple testing procedure for the fact that you have 2 different treatments to compare, but not doing a multiple comparison on the endpoints looked at. And this leads me to my conclusion, and we'll have a lot of time for discussion. So what I think generalized pairwise comparisons bring to the armament of statistical procedures that we already have is that it does increase the flexibility of the analyses. There are many ways in which you can generalize the Wilcoxon test, and so some of them are extremely interesting, as I've shown. You can incorporate multiple outcomes in a single analysis. Now, that in a way that remains manageable. Of course, there are other multivariate analysis techniques, but I don't know if you've ever used any of them. I've studied them in my theoretical classes, never used them because they're essentially unusable. They make so many assumptions about what the data should look like in terms of their distribution that it's just not practical to use these methods in general. Sometimes they can be used, but not many times. You can incorporate thresholds of clinical relevance, and that's completely new. No other statistical method uses that approach. No other statistical method allows you to ask a physician what matters to you. Is it a 3-month survival difference or a 6-month survival difference? What's really important? And then do the test accordingly. None of the other methods that we use can do this. Oops, I'm sorry, I went too fast. The GPC approach may, as I showed in the example, increase power as compared with a single outcome, and also increase the clinical relevance. through this use of thresholds, but also because you can use that, you can look at multiple outcomes in the same analysis. Now, one thing that I did not dwell on, but I think it's very important going forward is, as you all know now, we talk about patient-centric clinical research. We want to involve the patients in trial designs, trial analysis, trial interpretation, independent data monitoring committees, and so on. Everyone is about, how can we include the patients in the process? Because after all, we do this for them. All we do in clinical research is to try to improve the patient's fate. And so it seems to me that the statistical methodology should also use their preferences, and we can easily do this with GPC. We've shown this method to patients or to patient advocacy groups, and they just fall in love with it at first sight because they say, this is what we want. This is exactly what we want. Not these kinds of abstract methods that we don't understand anything about. This is, intuitively appealing. And finally, and importantly, the GPC approach provides a unique measure of treatment effect, in this case, the net treatment benefit, that is meaningful to patients and caregivers. Again, because the method is so simple, you can explain the method and then people understand, what it means to have a positive net treatment benefit or a negative net treatment benefit. So I will perhaps stop there. I had some other slides, but I really want to keep to time and have enough time for discussion. So I'm going to stop here, and perhaps the PDF that will be distributed has some more slides on where GPC can be used.